Okay, welcome back to Scientist Arena. In this video, we shall be talking about dimensional analysis 2. I already gave an explanation on dimensional analysis, so today we shall be trying to solve problems that have to do with dimensional analysis. So here we have a problem that says that the velocity v for the streamline flow of a liquid in a small uniform tube depends on the radius r of the tube, the density p, and the coefficient, the density rho, and the coefficient of viscosity eta of the liquid. Use the method of dimensional analysis to obtain an expression for the velocity, given that v is equals to r square p divided by 4 eta l, where p over l is equals to pressure gradient, and obtain an expression for the dimensional constant k in your expression of v. Alright, so first thing we want to do now is we want to identify the parameters involved. So if we were to identify the parameters involved and break them down to their own dimensions. So first off now we have velocity. We have velocity v. Alright, so velocity we know is equal to displacement over time. Alright, so displacement measured in length, alright, and time in. Alright, that's for velocity. Then the next one we have for density. And we know density is equals to mass over volume. So we have that as m divided by l raised to the power minus 3. Then we have we had radius. Radius just has to do with length. Alright. Then we have coefficient of viscosity. Coefficients of viscosity. Eta, which is equal to, that's force times distance over area times velocity. Alright, so that would normally, for force we have ml to the power minus 2 times distance we have l, all divided by area we have l raised to power 2 times velocity we have l to the power minus 1. Alright, so with this we have it as m, l here cancels this to l, we are left with 1l. Alright, then t here, t there, we are left with t raised to power minus 1. That's for coefficient of viscosity. Alright, so now dimensional analysis, let us now go down into it. So it says it depends on the radius, that's v now. V now depends on the radius of the tube, the density, and the coefficient of viscosity, eta. Alright, so we can introduce a dimensionless constant. We are introducing a dimensionless constant which is k. Alright, so we have our x here, for this we have y, and for this we have z. Alright, so now let us now go down into finding the dimensional analysis of this. So for v now, we have velocity v to be l t minus 1, right? Then we have k, we said k is dimensionless. Alright, then for r, we have length, and for rho, that's for density, we have ml minus 3, that's for y. And then for our eta, coefficient of viscosity, we have m l minus 1 t minus 1, and that's all for z. Alright, so now what we have to do is we have to equate the thing on both sides. Right, so now when we are equating, you can see this is the left hand side, and all this is the what? Right hand side. So now you look at the left hand side and the right hand side, you look at the one that is, for example, in the right hand side we have l occurring 3 times, l, right? Then we have m occurring 2 times, m, then t occurs only once, and yet t occurs only once. So we start with the one that is least occurring, which is what? T. So we have for t equating, that's equating the left hand side and the right hand side. So for t now we multiply by the power here. All right, so you should know that law of indices. So for t we have t, here we have minus z to be equal to, on the left hand side we have minus 1. All right, so minus cancels minus, we have that z is equal to 1. All right, so the next least occurring one is m. All right, so for m we have here that this is minus 1, so we have for m y plus, here also we have z is equal to, here we have no m, so that's 0. All right, so we have that z is equal to 1. Right, so we are simply saying y plus 1 is equal to 0, therefore y is equals to minus 1. All right, then for l, now we have for l, on the right hand side we have x plus minus 3y plus, here we have minus z is equal to, then on this side we have 1. All right, so here we have x plus, where you see multiplication you add, then minus 3 times y is minus 3y plus minus, that's l, minus 1 times z, which is what, minus z. And on the left hand side we have 1, right? So we equate it to 1. Then our x, so let us open the bracket. We now have x minus 3y minus z is equal to 1. All right, we found z, we found y, so we now have x minus 3, our y is minus 1, minus our z is what, 1, right, is equal to 1. So we now have x minus 3 times minus 1 is plus 3, right, and then minus 1 is equal to 1. So we make x the subject of formula. We make x subject of formula, we now have it as x is equal to 1 plus 1 minus 3. So x is equal to minus 1. All right, that's 2 minus 3, which is equal to minus 1. All right, so for this, we've gotten our x, y, z. We now have to put it back into the equation. So back into the equation we had was v is equal to krx rho y eta z. All right, so now let us input it. For v, we have v is equals to k r, x we have minus 1. For rho, that's our y, we have minus 1. And then for eta, which is our z, we now have 1. All right, so that gives us, if we were to put it in a simpler form, that gives us v is equals to k n over r p. All right, so this is it. Now they also say we should obtain an expression for the dimensional constant in your expression of v, given that v is equals to r square p divided by 4 eta l. Right, so we now have this, still have this. This is rho, not p. This is rho is equal to, here we have r square p, all right, over 4 eta l. All right, so here we are going to cross multiply. We are now looking for k. We are looking for k now. All right, so we are going to cross multiply this. We now have k now. This is a p. All right, so when you do it all together, we now have 4k l is equal to r cube p then rho, right, p then rho. So making k subject of formula, now we have r cube then p divided by 4 eta square l. All right, so that is our answer. Thanks for watching. See you in the next video.